Hello, hello everyone. I am Janmajya, and as you can already see, that I will be talking about open problems in FHE. Um, but before we sort of like go into open problems in FHE, I think it's worth it to sort of go over the reasons that we were able to come up with these problems, like the motivation behind these problems, because the problems differ from applications to applications. So it is worth finding out how did we arrive at these problems. At Gauss Labs, Phantom Zone, what we really want to build is something called globally mutually trusted third party. What is this party? Well, this party sort of guarantees three properties to everyone. The first property is that any information that you send to this party, it will always keep that private. It will not send it to anyone else. The second thing that it promises is that all the state that it has accumulated over time, we have been sending this party all our information. It accumulates certain state. It would never allow anyone to poke in it. So the state it has accumulated always stays private. And the third property that it guarantees is that we can ask it, all of us, some of us, can ask it to evaluate some function on the information that we send to this party. It would evaluate that function only if it has certain authorization from each of us. And it would only output the things that we want it to output. So these are the three properties that this particular party guarantees. I usually like to, instead of calling it, this mouthful of globally mutually trusted third party, I simply call it globally mutually trusted shared computer. And this is also known as the Gauss protocol, if you're familiar with an examples 1987 article about this. So we really want to build this out. And it was the reason that we built Phantom Zone, if you're familiar with it, it's a framework to sort of do multi-party computation. But the reason that we started building Phantom Zone is that we want to power this Gauss protocol. And while doing so, we realized that at the moment, Phantom Zone in its current state is only an abridged version of this protocol because it guarantees these three properties to only a certain number of people. You can choose the number, but it will only be for those number of people. It will not be global. And we cannot go global at the moment. And for this, in this abridged version of the Gauss protocol, we use Phantom Zone. Inside Phantom Zone, we use something called multi-party FHE, which brings us to the main topic, which sort of like tells you the source of the problems. Because we were using FHE for doing multi-party computation. And most of the problems that I'll highlight here would be somewhat related to FHE, but as well as related to multi-party computation. Okay, but before, I'll quickly describe what is multi-party FHE. Well, the key idea is that you take, so if you're familiar with FHEs, there is a secret that is held by a client, right? The secret is held by the client, and they encrypt whatever information they have, they send it to the server evaluates and sends it back. The key idea in multi-party FHE is that this secret is now split among the parties. Whosoever is participating in this protocol, it is now split among all these parties. And we usually refer to this as the ideal secret key. And literally, the ideal secret key at the moment is addition of the secret shards that each party has. Over here, we have three parties, but you can name the number. It could be like 100, 200, 300, whatever that is. And the step one is that all these parties come together to generate the public key, which we usually refer to as collective public key. It's a protocol. And then all these parties encrypt their private inputs using this public key and produce an FHE ciphertext. And as you would realize, since the private inputs are encrypted under the public key, under the ideal secret, because they use the public key to encrypt it, the ciphertext is encrypted under the ideal secret key. So the server can evaluate on all these ciphertext any arbitrary function, could be anything, and produce an output ciphertext, and then in the last step, all these parties come together to decrypt the output ciphertext. They come together and produce a decryption share for the output ciphertext and finally decrypt the output. And this is the reason why we cannot go global. This is the reason why we need these parties. Okay, now problem one. The first problem that we are facing at the moment is like we need a lightweight MPC protocol to generate bootstrapping keys. What do we have at the moment? Well, right before this, I described you a two-round protocol. First, you generate the public key, and then you encrypt your inputs. There exists a two-round protocol in Phantom Zone at the moment. There is also a one-round protocol that we came up with called non-interactive multi-party FHE, where the client comes online, just shoots a message to the server, and that's it. The problem with these protocols is that these protocols only generate a bootstrapping key, of which the ideal secret key has a higher norm. I'll sort of like tell you what that is. So let's just say my secret shard, the secret that I have, is like 010101. It's a vector of binary. Your secret shard is 010101 as well. If we add a secret shard, it would not be 01001 anymore. In the worst case, it would be like n. Every element can be n. And this is what exactly happens in this protocol, which is why we have to modify our bootstrapping operation to accommodate this peculiarity of the MPC protocol, which is why we need to make sure that our bootstrapping operation that we do in FHE is takes into account that any secret element inside the ideal secret key can be as big as n number of parties. And we eventually pay, in performance penalty for this. Like the bootstrapping operation is roughly 1.5. I would have been a bit optimistic here. I think it's 1.7 or to 2x in penalty. Okay, so what does an ideal MPC protocol look like? Well, it should be a lightweight MPC protocol to generate a bootstrapping key with ideal secret key that is binary. Why binary in particular? Or why some fixed property? Because, well, when you have binary secret key, you can speed up your bootstrapping operation by a lot. I just realized that I've been saying bootstrapping a lot, and I have not described it. Well, to black box it, well, bootstrapping is a way of, okay, if you stretch it for a while, what you can do is that you can sort of imagine every FHE compute, every FHE function can only be described in terms of bootstrapping. So anything to do in FHE is like a lot of bootstrappings that you have to do, which is why that's the bottleneck in most cases. And over here, I'm only referring to binary FHE schemes. If you're working with arithmetic FHE schemes, that's different. Okay, so when you have binary secret keys, when the ideal secret key is binary, you can assume an additional structure on the secret key and thus speed up your bootstrapping operation by a lot. I would say it roughly gives us like 2x improvement. One of the schemes that allows us to do this is something called TFHE, which probably a lot of people here would be familiar with. And why lightweight and what's lightweight? Well, when I say lightweight, I mean that it should not be many rounds. A lot of developers using Phantom Zone at the moment are complaining that even 2 rounds are sort of like problematic for them. So I would say not many rounds. In practice, let's just say, if we stretch, 2 to 3 rounds should suffice. I would say, to put an upper bound, probably 100 megabytes of in total communication from the client should be okay, but even that is a lot in practice, I would say. If your clients are, mobile devices, 100 megabytes is a lot as well. At the moment, Phantom Zone sort of like has 1 to 2 rounds, as I said, like non-interactive MPC and interactive MPC. And the communication is roughly 70 to 100 megabytes. We're trying to reduce it, but we're not there yet. Okay, problem 2. By the way, before I sort of like tell you this problem, amortized bootstrapping, I was informed yesterday that this problem is somewhat solved. In the sense like there are new results that sort of like solve these problems in a way that I would like, that I'm comfortable with. But I'll still describe because there could be further results as well. Okay, first, what's bootstrapping? I already described it, but I'll describe it again, just to give you the context. Well, the way I think of this is that, okay, so I suppose you're familiar with FHE ciphertext being noisy. Any FHE ciphertext you take, it has noise in it. And once you compute on the FHE ciphertext, the noise increases. And that's a problem, which is why we need something called bootstrapping to refresh this noise to a smaller value. And if you working with binary schemes, when I say binary, I would say they work with, Boolean values or at most 3 bits, 4 bits. And they're different from arithmetic schemes. These are different schemes. I will not be talking about it today. So when you're working with binary schemes, their bootstrapping operation is somewhat special. What you can do is, like, while you bootstrap, you reduce the error. And you can evaluate an arbitrary function on it, on the plain text itself. So you get 2 things. You reduce the error as well as you can evaluate an arbitrary function. And any FHE ciphertext that you can imagine, any FHE circuit, when I say a circuit, you're writing a function and you're representing that function as a circuit. Any FHE circuit that you take, you can represent that FHE circuit in terms of just bootstrapping operations, just simple bootstrapping operations. So as you would realize, if your function is big, you will have many, many, many bootstrapping operations. Which is why bootstrapping, is somewhat the bottleneck. Well, I wouldn't say that bootstrapping is the bottleneck because a polynomial sort of come in everywhere, but I would say in FHE world, you just think of bootstrapping most of the time. So what is amortized bootstrapping? Well, the idea is pretty simple. You take a bunch of Boolean ciphertext, Boolean FHE ciphertext, and instead of paying the cost of, let's just say you have n Boolean ciphertext, instead of paying the cost for n Boolean ciphertext to be bootstrapped, you just try to pack them into a single bootstrapping operation. You amortize the cost of n Boolean ciphertext bootstrapping into a single bootstrapping operation. And I think that doing so would significantly speed up FHE runtime, because when you try to compile any function down to FHE circuit, there are many stages where you can sort of like take advantage of the optimization, because a lot of the functions, FHE in general is very parallelizable. Like all the FHE circuits sort of like have exponential growth, which means they're parallelizable. So if you're able to do this, then we sort of like save a cost and we sort of significantly boost up the runtime of FHE. There are 2 main approaches at the moment. The first one is homomorphic RLW decryption. Don't worry, I'll describe it. Another one is using CKKS, which is somewhat interesting because CKK is an arithmetic scheme, and we're trying to use it for something to speed up in the Boolean schemes. So what is homomorphic RLW decryption? Well, if you're familiar with learning with errors, which is the basic hardness assumption that we make in FHE, it's like the hardness thing that comes from, like that gives you the cryptography of FHE. You take that, so learning with errors over vectors. We sort of port it over to polynomials because that's what you usually do when you're a cryptographer. You sort of take LWE and put it over the polynomials, and that is called RLWE, ring learning with errors. And what we essentially do is that we take all these LWE ciphertext and we put them into the coefficients of the message polynomial of this RLWE ciphertext. And RLWE ciphertext is big. Its message is again a polynomial because it's a polynomial ciphertext. We put the LWE ciphertext and sort of like perform some transformation, which is very cheap, so that it is in the coefficients of the RLWE ciphertext. And then we homomorphically decrypt this RLWE ciphertext. And doing so requires polynomial multiplication, which, as you would realize, homomorphically in encrypted domain is somewhat expensive. But it turns out we can still do it. You can still do it, and it will give you an output ciphertext which has reduced error if you sort of take it out again. But the problem with this approach is that this approach can only reduce error. So you lose that good property of binary schemes that you can also evaluate a function while refreshing the error. So you lose that property in this approach. The second approach is via CKKS. CKKS is, I would say, it's an arithmetic scheme that works with real numbers. That's magic. Cryptography, the moment you hear real numbers, that's somewhat magic. The way it works is that CKKS is again an LW ciphertext. You take an LW ciphertext, a bunch of LW ciphertext, put them into the slots of CKKS. When I say slots of CKKS, well, CKKS has the capacity to sort of work over vectors instead of just working with polynomials. So we take all our RLW ciphertext, perform some transformation on them, which is again very cheap, and put them into the slots of the CKKS ciphertext. And then we come up with a function that approximates to the function that we want to evaluate. Let's just say we want to evaluate let's just say sin x, right? So we'll come up with a polynomial function because CKKS only works with addition and multiplication. So we come up with a polynomial that approximates very closely to sine function, and we evaluate it here. And this is a paper that's sort of like 2024, 1623, it's a recent result. They sort of give you a framework to do it for any arbitrary function that you want to evaluate. The good thing about this paper is that the polynomials they come up with is low degree, which means that you require less number of multiplications, which means that you can use better parameters. And I would say, I'm not able to recall what are the exact results, but I would say they're able to bootstrap 8-bit value, many 8-bit values, in roughly like 80 milliseconds, which is quite a problem if you just work with normal bootstrapping. It takes roughly a few seconds, I suppose. So that's a 3 orders of magnitude improvement, I would say. Okay, now we're done with homogeneous bootstrapping. Problem 3, FHE RAM. If you are trying to develop any application with FHE, RAM accesses are a problem. I'll tell you why. When I say RAM accesses, I mean that you have a memory and you want to access a single element from that memory. Right? Random access memory are a problem. Let's just imagine this game. And imagine that this entire square grid is encrypted. This is black box to us. And we really want to figure out where a frog is, right? How do we do it in FHE? Well, in FHE, you'll go through all these squares and check where a frog is. So if this particular map is really big, you have to pay the cost of traversing all the squares, which means that the cost is linear. And that's quite expensive. If you want to work with big memory, that is also quite expensive. And for any non-trivial application that's expensive, we have been developing a game. And that's sort of like, this is the main bottleneck for that game, honestly. We had to put in many cores, 5 servers just to get rid of this problem. But if you're able to make it trivial, then this wouldn't be any more problem. And if you sort of like intuitively look at it, it would say that this is impossible to do because, if you're able to find your frog, well, I shouldn't have frog, but like if you're able to find a particular element without paying the ON cost, without going through the entire memory, they're essentially leaking something. But turns out that this is not the case. There's something called doubly efficient random access memory or doubly efficient PIR. And doubly efficient essentially means over here is that you can do some sort of pre-processing on your memory so that each query is roughly log n. Well, the real value is like polylog n, but like we can assume it to be log n. Logarithmic over n, which is very cheap. But breaking with the reality, this approach is very expensive at the moment. I don't think that it's practical at all. There are implementations. So this was the paper 1703 sort of introduced this thing. This is the paper that sort of implemented this thing. They sort of made certain improvements. They've brought it down to certain realms of practicality, but it is still far away. But this is an important problem because to use FHE for any non-trivial application, you will need to solve this problem at all. Okay. Now coming to the fourth problem, which is a well-known problem in blockchain world, verifiable FHE. And the reason that the reason I'm putting this as the last problem is not because it's less important, it's because, people know about this really well. People in blockchain space know about this really well. And in blockchain world, what we've done is that we've patched this problem by having multiple servers. You have multiple nodes, and we make them agree on the output of the FHE circuit, and if and only if they agree, they would be able to decrypt the output. That's good, but I think verifiable FHE is still a very important problem to solve for the next generation of cryptography, which is I/O and program obfuscation. And that's it. Thank you. There was a QR code here that is not visible. If you want to learn more about Phantom Zone, just go to phantom.zone, and you'll be able to find things. There was a QR code here, which is not visible anyways. Yeah, yeah. Yes, Gauss _labs. There's also a site, phantom.zone, and that's it.
Anyone else? Any questions? Okay.
For this kind of trusted party, does it help if we can eliminate somebody if they are not there for a long time?
We can, like, I suppose you're talking about liveness. Yeah. I think we can. It depends from application to application, which is why I would say at the moment that's a problem. Like, if we, like, assuming liveness on parties is a problem.
So my question is, like, since it's easy for people to join,
Yeah.
but like in real case, even like after a few thousand people join, but the active user is probably like 20.
Yeah.
So it might helps, like we can prune for a while for this inactive people, just remove them out to help with efficiency.
That is true. That would help, but that's not possible in practical realm at the moment.
Okay.
Because these people have participated in the secret shards, and they would have to they would have to again interact and be like, okay, fine, I'm no more participating in this case. If they do not do that, then that's not possible. That's not possible. What you're saying is not possible. We need to solve that problem eventually to scale this, but it's not there yet.